Good morning, good morning. So I'm Harald from research, and I'm going to give an overview of the kind of work we do at Comma. So our stated goal at Comma is to build a superhuman driving agent, which is basically a level 5 self-driving car. And I'll talk about the way we're trying to achieve that. First, I'm going to test my pointers. Right, that works. Oh, that did something. So before we can talk about how to build a self-driving car, it's important that we have a very clear definition of what it is that we're trying to achieve. So to build a real self-driving car, I think the first obvious thing we want is that it doesn't crash. Crashing would be bad. We can't expect it to never crash because that's very difficult. So crashing less than an average human, I think, is a good minimum goal. Another problem is that you also want it to get you somewhere. If it doesn't get you anywhere, it's not that practical. And for it to be really useful, we want it to drive on basically all the roads that a human would have no problem navigating. So just your average driver with a driver's license, our self-driving car should be able to do the same things. It shouldn't, I don't know why that happened. It shouldn't satisfy these things just by being super slow and avoiding hitting anything just by driving 5 miles an hour. So it should be somewhat efficient so that humans don't get frustrated by using this. And then the last point's a little bit more nuanced. We want to build a self-driving car that doesn't require any infrastructure at all. What I mean by infrastructure is we don't want to have to change the lane lines or the road or change the traffic signs and change the traffic lights. Also, it appeals a little bit more to our self-driving system. We want something that works exactly on the roads that humans can drive on now. If it can't do that, you're basically just building a train in a slightly different format. So no infrastructure. Okay, so first we'll think about the classical approach that people use when building a self-driving car. It's kind of seen generally as a robotics problem where you have some environment. In this case, you've got the road, and then you've got a whole bunch of sensors that tell you things about this environment. You've got cameras, radars, in some cases LiDAR, IMUs, and all these sensors go into some perception layer. This perception layer can analyze what these sensors are doing and can process it in some way. In many cases, you have machine learning models running that will parse the camera data and tell us some things about maybe where are the lane lines, where are the other cars, where are pedestrians. All this information then produces some perception output, which is a list of things that you think might be relevant for driving, which is, like we said, lane lines, where everything is, where the people are, where are the traffic lights. And then this would go into another layer, which is the planning layer. The planning layer is generally some kind of hard-coded optimizer that tries to optimize several different goals, which is like, don't hit things, try to get somewhere, follow some traffic rules. And then the planning layer outputs some trajectory that you expect the car to drive, which is then executed by some kind of control system. Robert talked earlier about what that control system kind of looks like, and here you can see the steering wheel turning. So we'll look a little bit more into what one of those perception systems would be. Here's some examples of things people use for self-driving cars. So you've got a machine learning model that just looks at the video of the road, and it's labeling all these things that might be relevant, which is like cars, people, traffic lights. It's probably also, you've got systems that label all the lane lines and the sidewalks. It's labeling the bus as a different thing as a car. And then you can compile all this information together with some other sensors, maybe like LiDAR, into this 3D representation of the world, where you've got all these cars, all these lane lines, you know where you are, and you know kind of some version of what the environment looks like. Once you have this perception output, let's go back one, if I can. Oh, yeah, there we go. So we have just a classical planning layer. You'd have some objectives that you try to stay, so like stay in your lane, don't hit other things, don't hit cars, stop at traffic lights. And let's give an example here for this scene. How do we do that? Well, it's pretty easy, right? You just drive straight, stay away from the other cars, don't try to go over the lane lines. So this seems pretty easy to write an optimizer that can satisfy those requirements. Then we go to the next scenario. Here, this is a little bit more complicated. Oh, no, let's go back. Where we have an intersection, and let's say we want to turn left at this next intersection. Now, you're trying not to hit things, you're trying to stay in lanes, and you're trying to stop at traffic lights. Now, this all doesn't seem like much of a problem. The light's green, so you can drive through the intersection. That lane's open, so you can just go over there, drive there, and then you turn left at the next intersection. That doesn't seem that hard. We can write some code that does that. But if we zoom out a little bit in this scene, I'm really confused by which button does which on my clicker. The top one goes forward. Yeah. Oh, there we go. All right, so we zoom out a little bit in this scene, and there's a pedestrian standing on the crosswalk. Now, this person looks like he's paying attention, and it doesn't look like he's going to cross if there was a car driving, but we still kind of want to keep a safe distance. You know, our optimizer has a target, which is don't hit people, so we try to keep some distance from all the pedestrians that we're trying to avoid. But what does that actually mean? You want to drive in this left lane, you want to keep some distance from this person, but you also want to stay in the lane. So what's the compromise? Like, are you going to drive in the middle of this lane, or are you going to drive a little offset? There starts to be a lot of these competing costs in this optimizer, and it starts to be very confusing how you tune this to get a desirable trajectory. Personally, I would just drive in the left lane and stay a little bit away from this person, and that'd be fine. But it's hard to actually implement these compromises correctly. And then if we change the scene a little bit, and imagine it's a child that just dropped his ball. For me, this would completely change things. I would not go in that lane, and I'd keep way more distance. But this introduces a new problem, which is that our perception layer doesn't output whether this is a child or a normal pedestrian or a child that's holding a ball or just dropped a ball. So now it's kind of unclear how we can write policy that deals with pedestrians correctly, because pedestrians can encompass all these different things. And the more of these kind of more complicated scenes we look at, the more and more we run into these edge cases that we really have no idea how to deal with. So that's the classical approach. It honestly seems like the back button works and all the other ones don't. So the flaws with this classical approach are that you require machine learning models that do perception based on some camera stream or some LiDAR stream, and generally these are hand-labeled. That's very resource-intensive and not very practical. The planners are some hard-coded optimizer logic, which generally has to have code for a whole variety of different scenes and environments, and this list grows and grows as your system becomes more and more capable and has some unbounded complexity. And then there's the other problem, which is that the planners need to take in information from the perception model, and any list of things that we can come up with that we think will be good enough for the planner tends to be incomplete. We always run into some new edge cases and actually need to add new information, and this list of things the perception model needs to output also grows endlessly. So the result is you have this stack which is massively complicated, impossible to maintain. And this is why you see many self-driving car companies that use this approach make a lot of progress for a few years, and then they start to stagnate because they're working on this huge stack that is so difficult to alter because of how complex and intricate it is. So what can we do? A friend of mine used to say, every time you get in a car, you show it how to drive. The problem is that it forgets. And this brings up a very powerful idea. Humans don't drive by memorizing some very long list of rules of how to act in every environment. Instead, they learn some basic traffic laws maybe, but in general, they observe how other people drive, they observe how their teachers drive, and from that, they learn how to operate a car. So we can very easily collect data of humans driving. So how can we leverage that in the same way that a human would to teach the system about how driving on a road works. So we call this an end-to-end approach. We can just build machine learning models that take in some raw sensor data, like video or other sensors, and can immediately just say, drive like that. So it's kind of like having video and asking a human, based on this video, where would you drive? So we can very easily collect this data set, and then we can show the model where the human drove and have it predict that. And then you have this system that will tell you where it thinks humans would have driven. And it's actually a very powerful idea because when you have a data set of thousands of users, then the model will predict where it thinks thousands of users would all predict on driving together. So it's kind of some consensus approach, which can be much more robust than just asking a single person where they would drive. And what's really powerful about end-to-end is that all you need to make it handle more complex scenarios is to make the models bigger, give it more data. And it will just become better and understand more. It doesn't require more code, it doesn't require hand-tuning some things, and it doesn't require adding extra logic for every new scenario we support. All we need is bigger models and more data. So given that, we can redraw the diagram and look at the new approach. So we've deleted the perception layer. All we have is raw sensor data. It goes into some big planning machine learning model that outputs where it wants to drive, and then that gets sent to some controls interface and operates the vehicle. It's now much simpler and should be far more scalable to actually dealing with the huge variety of complex situations that appear on the road. So to start, we need data, and we need a lot of it so that the machine can learn from it. OpenPilot collects data from all over the world in 1-minute chunks. We collect currently over 100,000 minutes a day. Collectively, it's over 50 million miles of data collected, and that equates to a few full lifetimes of driving. Humans can learn how to drive in a few lifetimes, so it doesn't seem unreasonable to expect that under some conditions, a machine learning model can too. On the right, you can see just a couple of weeks of data collection from the United States. You see we have a pretty widespread data collection across the entire country. I think there's some AI in this clicker. Oh, I see. All right, let's go. Oof. Maybe I should just stop for a while and let it catch up. Okay, that's the one I wanted. That's the one I wanted. Great. So just to give some examples of how really diverse this data set is, I just made this quick tool where you can click on the map and it'll show you some video that's the closest. I picked some places I thought would look cool. So we've got the Golden Gate Bridge, Utah, Joshua Tree National Park, San Francisco Bay Bridge, New York City, the Colorado Mountains. And so when it's exposed to all these scenes, our model can learn about how driving works in all of these different environments. This is some international data. We've got Thailand, some rural roads in Scotland, Nigeria, Belgium, Singapore, Taiwan. So you can see driving is really different in all these scenarios, and it's very important that we have this massive amount of diversity in the data set. So the machine can start to understand what's different between driving on some farm road in Scotland where you drive on the left and driving on some cobblestone street in Belgium. So we've got the data, and now we want to start thinking about how we train this model. We want to clearly define what the output of the model will be. We talked previously about how the model is going to output some path of where to drive. This path is going to be in meters. It's going to say, over the next 50 meters, turn a few meters left, or turn a few meters right, and after that, straighten out. Getting this information about where a human drove in this representation for all the video we have is actually not trivial. We need a localizer to do this. So a localizer answers the question, where am I right now? Where am I looking? Where am I going? And where did I go? once we can answer those questions, we can then generate the ground truth for our machine learning models. On the right here, you can just see some satellite view overlaid with some images we use to represent cameras of video we've taken. So these are just 4 parallel lanes somewhere in the Bay Area. So to build a localizer, we start with GPS, or if you want to call it all those constellations, including the Chinese and the Europeans, who call it GNSS. GPS doesn't exactly tell you where you are. It has these satellites orbiting around the world, and it tells you kind of how far away every satellite is from you. If you know that, and you know where the satellites are, you can then kind of estimate where you are. And this is what most GPS receivers do. The thing is, they use pretty simple algorithms with not that much compute to do that. When satellites tell you how far away they are, there's a lot of error in this measurement. It can be influenced by the humidity of the atmosphere, by the relativity errors in the satellite's atomic clocks. It can be influenced by things in the just ionization in the atmosphere. And so we can get quite a bit more accurate results if we just take these raw measurements and do our own processing. So we built an open source project called Leica, which is capable of doing all this processing, and we can get much more accurate results. One of the cool things that we can do by having our own library is we also get the Doppler shifts to every satellite. Doppler shifts, you can measure the difference in frequency that you're seeing from a satellite, and it will tell you the relative speed of your receiver to the satellite. And this actually gives you such accurate speed readings that the GPS gives you far better speed readings than the speedometer of your car. So this is very useful for the kind of localization we're trying to do. One of the examples of things Leica can do is if there's activity on the surface of the sun, this ionizes the Earth's atmosphere and can cause a few meters of localization error in any normal GPS receiver. We can download some reports from NASA that tell us about this solar activity and compensate accordingly, making our localizer even more accurate. So we've got raw GPS measurements that we processed a little bit, massaged a little bit to get low errors, and we can use that to get a location and to get speed. But it doesn't tell you where you're looking. It just tells you the position, not the orientation. Another problem is that GPS is great, but not always. When you're under trees, in a tunnel, in a parking garage, GPS either works worse or not at all. So to be able to have ground truth in all driving scenes, we want to have a system that always works. So it needs to work when GPS is spotty, and sometimes even when GPS is not there at all for intermittent periods of time. So we want to do sensor fusion with redundant sensors. We made an open source project to do this. It's called RedNose, and it's a pretty large Kalman filter, which is a type of optimization filter that takes in all these different measurements, including GPS, and will output its best estimate of where you are and the orientation of your vehicle. So we use IMU data here, speedometer data, but the most important is actually camera data. So we can look at the video of the dash cam, and we can see how things are moving in the scene, and we can track those with things called orb features. And we can use those pieces of information in our sensor fusion system, and it'll give us accurate information about not only where we're going, but also what orientation we have, how the car is turning. If you have very accurate localization of both your orientation and position across many frames, you can start to stitch things together. So here you can see kind of a cool example of how well our localizer works. We take all these points that it's seeing while driving along this road, and you project them all down, and you see this beautiful top-down view of you passing an exit, but staying in your lane. And its localizer is very accurate, and that's great, but the most important thing about it is that it is robust. Oh, no. It needs to work in all the situations we want to expect our car to drive, which is all of them. So it needs to work when the scene is dark, when there's not many things going on, not many features to tell you about where you're going. In this case, we still have a sign, but once you pass the sign, really, you've just got a couple lines on the road, and this can really confuse the camera odometry system. This is actually an example of a bug we had only a few releases ago, where if the lines were continuous, then it would match features to itself and get super confused and start cutting the turn. But that's now been fixed, and so far the system has become incredibly robust. So now we've got ground truth. We know where the human drove for all this video we have. So all we have to do is we train a neural network that takes in a couple of frames from the video. We just use 2, and predicts a path of where a human would have driven in that situation. Here you can see the system training. It's a little bit noisy at the end, but it's already getting right that you have to go mostly straight. The model we actually use is an efficient B2. Takes in the images here, which are that size, and then goes to some head and outputs this path. Oh. No. OK. So we've trained our machine learning model. And now it's time to find out whether it works. So generally in machine learning, you have some training set of data that you've worked on. And then you've got some other data that you keep separate to test on, just to make sure that it's not overfitting. So we've got all these examples from our validation set. And we look at them, and it looks pretty cool. We've got some lane lines in there as well. That was easy to do, so we just added those. And you can see it turns there. You can see it even gets the 3D parts pretty nicely. Here it's predicting it's going uphill and going over a crest of a hill over there. But in general, this all looks pretty good. This looks like what I would have labeled if I were to say where to drive. So we're ready to try it out on a car. So we take this model, we implement it, we make it so that its output is executed by controls, and it doesn't work at all. We drive on it, it completely drifts out of the lane almost immediately. So there's this quote about software engineering that I think is really applicable. We do these things not because they're easy, but because we thought they would be easy. And so this applies here too. But this brings us to, what can we do now? We thought it would work. It looked like it worked on the data we tried it, but in the real world, it fails completely. We could keep trying things and then try it on a car, but this is very time-consuming and gives us a very, very slow iteration speed. So we want to have some way to test it offline from our desks before we go out and try it on a real car again. To do this, we would need a simulator, so that in the simulator, the model can predict where it wants to drive. We can have some simulated control system execute on that trajectory, and we can then see how it behaves. Hopefully, if the model is driving on its own path, and this is simulated in full rollout, we should start to see similar results we saw in the real world. So what kind of simulator can we use? You can use things like GTA 5, or Carla, or Truck Simulator. I mean, there's roads there, and they look kind of all right. But the problem you get with those kind of simulators is very similar to what we talked about at the beginning. The amount of environments and scenarios one of those simulators can simulate is always going to be limited to the amount of scenarios you engineered into it. It's never going to capture the full diversity of human driving. If you want a self-driving system that can work in Nigeria or in the country roads of Scotland, you also need a simulator that can represent that. Otherwise, if it fails there, we'd never know about it. So we want to build a simulator that is based off real data and can simulate the entire spectrum of our data set. So we use a little bit of a trick, which is you just take video, and you can just warp it a little bit left and right, make it appear as though you're driving in a different location than you actually did. You can see as it's moving around in the simulator that things are warping a little bit. And obviously, if you go very far from where the video was taken, there'll be nothing left. But this simple trick seems to be good enough to do some simple simulations. And those simulations tend to be good enough. So let's try the system we just trained in one of these simulators and see what happens. So on top, we just have this segment of driving down a road behind a truck. And we have the model that predicts your path, and we try to execute that plan. You can see it kind of already starts to drift out a little bit. But in reality, it started to drift out much, much, much quicker than that. And then we realized this is because in the real world, there's a lot of disturbances that act upon the car. There's little bumps in the road. The tires aren't perfectly aligned. And there's things like wind gusts. And all these things push the car around a little bit in a way that the model didn't want it to. So we can simulate those disturbances too, and this is what you see in the bottom frame, and you see it drifts out in a matter of a few seconds. Now, this is exactly what we saw in the real world. So trying to understand what is actually happening and why just having the model predict what it thinks a human would have done in this situation isn't enough is kind of difficult. It's something we argue about a lot, and it's worth the whole discussion in itself. But I'll try to give as clear of an explanation as I can, which is, imagine the car is on the right of this lane, so it's not perfectly centered. What would a human do in that situation? You could imagine that the human would probably correct and go back to the center of the lane. And this is probably true, but when would the human correct? You can see here it tries to correct a little bit at the end, but in the beginning it still goes straight. So if that's what's happening, and you have this car at time t0, which predicts to go straight and then recover, then tells the controls to do this. It goes straight, and it's still in the same position in the lane, and you ask it again, what would a human do in this case? But nothing has changed. So it answers the question in exactly the same way again. It says go straight and eventually recover. And if we run this in a loop, the system never recovers. It keeps predicting, just go straight for now, and at some point recover, because that's what a human would have done. But with nothing keeping track on the fact that it's never actually executing recoveries that it had in mind, it just continues to accumulate error, and if there's any amount of disturbance, like wind pushing this to the right, it'll just drift out of the lane. And so this is what we see in the real world, and it's also what we see in the simulator now. Oh, almost. So how do we solve this? Like we mentioned, really the problem is that the model is never learning to recover from mistakes. It gets pushed out of where it wants to be a little bit, and it doesn't recover. So one of the ways we can solve this is by training directly in a simulator, in the same simulator we've been talking about. Push the model left and right a little bit, introduce these disturbances, and tell the model, recover right now. And that's what you can see in these GIFs right here. So we've got the black path is where the human actually drove in this situation. And we push the car around a little bit, and we tell it, that's where a human was driving. Get back there immediately. And that's what you see the white path is, which the model is predicting. So you're seeing we're pushing the car around, and the model is seeing that, and it's shifting this path to where the human was driving. You can see the same in this situation. There's actually a lot of details involved in getting training in a simulator like this to work, and that's the culmination of a few years of work at Comma. We've got some more technical write-ups about the details of that. But in essence, this is what it is. So we've got this new solution, and we think it might work. But how do we know if it works? We already talked about the importance of testing before, because we don't want to test in cars. Testing in cars is super time-consuming. We actually have this rule at research at Comma that testing in cars is not allowed. If you can't reproduce it on your desk, it's probably not worth looking into. So we want tests that work completely offline and give us indications about how the model will perform in the real world. Everything that we don't track or test explicitly will probably regress or break at some point. We've experienced this through a lot of trial and error, and we are now very aware of the fact that every situation we want to work correctly needs to be appropriately tested. So we put the model through a whole series of tests. Give it a little eye exam. So I'll just give some quick examples of the kind of tests we can run that just give some indication about what's going on. The first thing is we can just ask the model how fast it's driving. We know how fast the car was driving. If the model doesn't know exactly its own speed, that's generally an indication of some kind of failure. We can also check the accuracy of how closely it's matching the path that the human was driving, how closely it's matching the predictions of some lane lines. If anything here looks weird or there's a lot of outliers, that's usually an indication of a failure that we would want to look into. We also have this simulator, so we can actually just let the system drive in simulation and do all kinds of tests of how it behaves. We can introduce lag in the steering rack and see how it reacts to that. We can introduce disturbances, such as wind. We can make the steering wheel offset pretty large so that it's just pulling left all the time. And we can see how it reacts to all these situations and kind of get an idea of how it would fail and how many disturbances are necessary for it to fail. So we drive the model in simulation on thousands and thousands of minutes of driving, and we see kind of what the overall results are. We check how often it deviates from the human path. We check, does it cut turns too much? Does it overshoot turns too much? Is it just kind of too aggressive all the time? And all these things we can find out by just doing metrics on thousands and thousands of minutes of simulated driving. So one of the other tests we do is we just check overall, when did the model predict to do something that is completely different from what the human actually did in this situation? So did the model ever predict something that looks like a swerve compared to what the human did? And here are some of those results of those tests. And as you can see, they're basically all lane changes. The human made a lane change, which is the white path, and the model predicted to stay in your lane. This isn't a bad thing, but it brings up this interesting point, which is that we expected the model to always output the right answer, which is what a human would have done, but that's not, sometimes there's more than one correct answer. Whether or not you make a lane change, both making the lane change or not making the lane change is generally acceptable, and it's definitely both safe. So we need to give the model some context so that it can understand how to deal with this. We need to make sure the model understands where it wants to go so that it can make a lane change if it's necessary, or turn right or left if it's necessary. Here's some examples of this happening. So you've got a human making a lane change past this car, and here you've got an intersection where there's a turn left lane and there's a go straight lane. And here, in this case, the person kept left to make the left turn, but might have just as well just gone straight. So to deal with this problem, we just have like a small set of hand-labeled classes, which is you can go straight, you can make a lane change, you can keep left, keep right, you can turn left, turn right. And we label those. We give the model that as context, so it makes sure that when the model's making a lane change, it's doing that when it's told to make a lane change. And then that brings us to there's really only one correct path given this information. So we fixed this problem by labeling that. You'll hear later in the talks a little bit more about how exactly we label that. And so this kind of works. And it more than kind of works. This is an end-to-end system that we've shipped, and since a few months has been running on OpenPilot. You can go into the settings and disable lane lines, and it will just work completely end-to-end in the way that we've described. This is, as far as I know, the only kind of end-to-end self-driving system that works at all, and it's definitely the only one that you can experience. So we'll just go through some quick examples of kind of the power of this end-to-end approach and things that it allows us to do. I think the button's sticky. I think that's what's going on. Oh, did I do that? Ooh. Wrong talk. But the clicker definitely has a mind of its own. Anyway, so quickly I'll give some examples of lane changes, which are one of the things that's possible with this end-to-end thing. We've told the model about lane changes during training, and so we can also tell it to do a lane change like a human would. Oh. I'll take a drink break while we're taking a break anyway.
The lane changes are too good.
Yeah. It's trying to keep it a secret. Trust me, the lane changes are going to be worth it when they're finally revealed. Yeah, we can talk about it in the Q&A as well, but All right, we'll take a short break. Everyone can think about the questions they're going to ask later. I guess this is kind of a good place to take a break. That was how we build it, and then we'll have the grand reveal of the results. Okay, I can take some questions right now, yeah. We'll do a couple questions until we've got the laneless results.
Model training takes a long time.
Yeah, somebody's trying to get the GPUs up and running.
Any questions? Harold, we have a question here.
Sure. So I saw on the slide you had an efficient net and then a fully connected layer. Mm-hmm. And that corresponded to vision and planning. Could you go a little bit more into, like, are they separated or are they all trained at once? Is there any separate training of those two model components?
No, it's just the architectural separation. So you've got the conv-net, which is, so the B2 is fully conv, and then you've got some dense layers on the bottom. But it's all trained together.
How many parameters on the bottom versus the top?
I don't know.
Or roughly?
Like
Just
a few million in the bottom. And I don't know how much an efficient net is. That's several million too. Oh, we're back. Back. Right, so this approach works. And we've got end-to-end machine learning working for self-driving. Here's the first example of this, is we've got end-to-end lane changes. So this system was never explicitly taught about lane changes, lane lines. It was never told that a lane change is crossing a lane line. We just teach it. These are lane changes that humans did. Try to do them like that. And in fact, these lane changes will work perfectly fine if there were no lane lines. If this was snowy or it was just a badly maintained road, lane changes would work just as well as they would for humans. Next example is just driving lanelessly in a variety of situations. So on the left, we've got a road that's completely snowed in. If there were lane lines, we can't see them. And a classical system would struggle here. There's not really much to go off. You could say that maybe the road ends there and you try to stay on the road. But a laneless system can clearly see this is where a human would have driven, because that's where the tire grooves are. And it can smoothly just do exactly what a human did. This is the power of the end-to-end machine learning. On the right here, you can see there's a turn to the right. And there's quite a bit of oncoming traffic that looks quite intimidating. And the laneless model does what a human did, which is cut the turn aggressively to avoid this oncoming traffic. Again, these are all just features that it can learn just by observing humans. We didn't ever tell it to avoid traffic. We didn't ever tell it to follow the grooves in snow. It's just observing humans and doing what a human would have done. So what about longitudinal? This entire talk has been talking about lateral control of the vehicle, which is just controlling the steering wheel. There's more than that to controlling a vehicle. You also need to control the gas and the brake. We've been working on this for quite a long time, and only the last few months have we really been able to ship laneless models that work well. And so that's been the main focus. But all of the lessons we've learned and all the strategies we apply should work perfectly fine for controlling longitudinal as well. So recently, we just started working on that, and I'll give some quick examples of what some end-to-end longitudinal features would be. So we've got model-based FCWs that was shipped a few releases ago. So we can just ask the model a question. You know how humans drive? Tell me if you think a human would brake in the next few seconds. And so that's what you see here. When the FCW pops up, the model is saying, whoa, I think a human would have braked hard here. And so this is shipped in OpenPilot. if you're engaged and you're in a situation like this, you'll get a warning from the model saying you might want to brake pretty hard here. Here's another example. So again, this model, we're never told it about cars explicitly or anything like that. We're just asking it, tell us when you think the model would brake, when a human would brake hard. Another thing we can do is we can ask the model, tell us where you think a human would stop. Again, that's basically the same ground truth as the paths. We just check where the velocity becomes 0 and a human driver becomes stationary for a while. So here you can see the model is predicting a stop line, which is where the human would stop, right by the red traffic light. And here you can see it by a stop sign. So this is completely end-to-end, seeing the traffic lights because it knows that's where humans generally stop. And the same with the stop sign. It's not explicitly looking at the stop sign. It just looks at the scene and knows a human would probably stop here. So what's next for comma research? Stop lines is one of the features that we haven't rolled out yet. That's the only thing in the talk that's kind of still experimental. We might want to ship that soon if we can get it to work pretty well. In general, we're really just looking at making these models bigger and smarter and understand more and more complex environments. So this is going to keep improving end-to-end lateral control. And then we also want to move more and more to end-to-end longitudinal control. Currently, OpenPilot still uses lead car detectors and just normal ACC commands to control the longitudinal control, and we want to start moving that to exactly the same full end-to-end architecture we're using for lateral. Questions?
And I don't think it's currently used in operation when OpenPilot is engaged, correct?
It is used for some parameter estimation of the vehicle controls, yeah.
So do you think that with your longitudinal control, you'll be placing a larger reliance on GPS in the future?
Not really. I'm not sure why that would be necessary. The model shouldn't require GPS for anything at runtime. Are you saying because you want to make a map of this places to stop or something?
Well, I don't want to be restricted to only where we have GPS mapped out roads. You know, one of the benefits of OpenPilot is you can drive on any road.
Right. So we do rely on GPS for ground truthing, but like I mentioned, we do support spotty GPS, and so the system should work completely without GPS. And so currently our data set should capture all the situations where GPS doesn't work. Just because if you had GPS 40 seconds ago, then that's enough to carry through to the entire chunk of data we analyze. So that's not a requirement.
I'm going to start with questions down the row here.
I want to ask how you look at training data and decide this is good driving. And by that I mean, what happens if in your training set you look at night and the driving in the area of this bar at night after 3 a.m. is kind of weaving all over the place, or a human tends to roll this stop sign, or somebody's just weaving on the highway, or quite frankly, you drive like I do when I'm not driving on OpenPilot. How do you get rid of all my driving data and train on the chill people?
So we kind of think about it as, you're not just looking at mimicking one person, right? We're looking at this whole data set. And we make the assumption that when humans make mistakes, they tend to do it in noisy, uncorrelated ways. And so if you have a system that behaves like it would the average or the median of thousands of different drivers would, that's generally a very good approach. If you asked 50 people to look at a video and exactly what they would do, the consensus of that should be very stable and I think good driving. If that ends up that the average driver is perhaps too aggressive, what we want OpenPilot to be, we can start doing some basic things to differentiate some aggressiveness and tune it down a little bit so it's a little bit more conservative.
I can see how that would work for most things, but just how would you control for, saying, rolling a stop sign, which, quite frankly, the average is going to show that a fair bit?
So right now we're just really not at the stage where it makes sense to think about things that detailed, I think. Okay. We first want to get to what an average human would do, and if for some reason we want the system to behave differently, we can think about that then, and there's some tricks to do some filtering of certain types of human behaviors, but I think average human behavior would be a massive victory for the entire self-driving space.
Hey, thanks again. Question here, how do you train out like unwanted behavior? One thing that I've seen with this end-to-end approach is sometimes car tries to follow what driver in front of you does. It kind of ignores lane lines. It just, if that car goes right or left, it just follows it.
Yeah, so that's kind of similar to Jason's question. And like you said, generally mistakes humans make are very noisy and uncorrelated. And so if you take the average of lifetimes of thousands of different humans, the behavior should be very consistent and should be pretty desirable.
Well, it's not really about mistakes, but if you look at it when human drives behind somebody, like we pass it.
Yeah, I mean, like I just said, I think average human driving would be a huge victory for the self-driving space. No system in the world is anywhere close to that. So that would still be much better than anything in the world.
Part of the following problem is big model, I think. Why it follows cars off exit.
Yeah.
Yep. So in regards to end-to-end lateral control, if you, let's say, had a camera on both sides of your vehicle, so you had a wider field of view and you were training on that, would the AI start to learn to move over to the left side of the lane if there's a semi on the right side like a human would, assuming there's no car on the left side? Or would that kind of get washed out in the training?
No, I'm pretty sure that would. Consistently, I think humans try to keep distance from cars next to them in highways, and so I'm pretty confident that model should learn behavior like that. You can actually see, in some cases, if there's a semi on the left side of the lane, the end-to-end planning will deviate slightly.
Awesome, thank you.
Yeah, so first of all, thanks again for the presentation. Super informative and amazing technology. Kind of like inverse to the two bias questions that came before, have you found either any places where it's relevant or where it's useful to have explainability backwards? Like if the model does something that's particularly weird one time, like it swerves out a particular type of lane or it takes certain types of exits, are you able to go back and tell what influenced the model to actually behave this way?
Yeah, so that's, I think, a very interesting question and something that when I started working on these things, was much more worried about than I am now. I think generally these models are seen as kind of these black box things that can behave in unpredictable or weird ways, and there's no way of explaining it. But so far, every case that we've seen of it behaving something that initially looked weird, we've been very easily able to reproduce and explain. To give one quick example of an issue we used to have is everything was fine, the roads looked fine, and it would sometimes randomly start predicting lane lines in the center of the road. And this was a bit of a mystery for a while, and then you start to look at the ground truth that has lane lines in the middle of the road, and you find there's some person that had like a fluffy thing at the front of his car, which was kind of colored orange, which was detected as a lane line. So this kind of made it into the data set, and then the model sometimes behaved that way. But so far, every single weird behavior we've seen, we've been able to explain. Same, yeah.
What's your intuition on continuously making use of larger models and keeping just sort of taking the traditional ML and just scaling it forward? Because in the case of real world, like you have distributional shifts. In that case, examples that occur very rarely would be unlikely for the model to make any sort of generalization on that sort of data. So how do you sort of augment the data, so make use of examples that occur very rarely?
I'd say so far we haven't really seen much of the issues with that yet. If there have been issues where the model struggles in rare cases of that, it seems to be that generally the model is just limited by the quality of our ground truth. If there's 0.1% of data that looks completely broken because of some bug, this will usually manifest itself in the model not being that smart in the end and not being able to see rare cases. But as we've improved the ground truth quality, even with the same size of model, we've seen the model become smarter and smarter and can learn more and more rare events. Maybe someday some kind of sampling would be necessary, but I think so far we're making very good progress without that.
Yes, so my question is specifically in regards to driver alertness. So one of the things that I've noticed that as I'm driving, there's some scenarios that I run into that I'm particularly on high alert. So I was wondering if there was any consideration with the comma team into developing a predictive model. Maybe you have different levels of alertness that could either be communicated to the driver or that you recognize as like high risk scenarios.
Yeah, so currently we actually have the model tell us how likely it thinks that OpenPilot would be engaged right now, and how likely it is that a user would take over from OpenPilot in the next few seconds, either with the brake pedal or the gas pedal or with the steering wheel. So the model already completely outputs all this information. We've thought about communicating this somehow, but just really haven't gotten around to it. But we do have tons of introspection in how much confidence the model has in that the situation is weird or that a human would start to feel uncomfortable.
Have you, and one follow-up question, have you thought about like creating a project for, kind of like a take-home project type of thing for where you could, let's say, you could export a CSV file and ask a few questions, and ask someone to like predict to develop a model like based on 10 data points or 20 data points that like, oh, if you think this would be more likely to be a high impact scenario. So like, say for example, you could go to an insurance company, look, here are the top 10 reasons for car incidents, and then you could have like specific questions based on that. So
Not entirely sure if I understand the question.
Well, just in the same sense that you have like, if you look on the website, you used to have the $500 bounty. So I was asking, like, was there any consideration, or would you consider like potentially having something where you took just some general instances and then you gave that as a project to the community that we could potentially work on?
I mean, if you're talking about developing on the model, that's kind of infeasible for anyone that doesn't have access to all the data and all the infrastructure that we use. So that's not something that's easy to distribute development on.
We got a question upstairs?
Hi. A question regarding the evolution of this approach. I mean, my impression that it can bring you so far, like what you do, but in building like a very nice L2 lane keep assist. But at some point, you probably want to go to, like end-to-end trained, unprotected left turns and go into the L4. And do you think you can push this approach where like you may like use the imaging data and the trajectory of the actual driver for training, or you'll have to do some like paradigm shift where you go to mu-zero approach and like where you have to rewrite the whole training pipeline?
So I think in general, this end-to-end training scales much further than any other approach. I mean, you mentioned things like mu-zero. It might be possible that a distribution shift of that level is necessary, that we can't use the simulator the way we do now and need something a little bit more advanced with some kind of learned simulator or other more advanced machine learning techniques.
But
Something
it's still,
like that.
but it's still like ideation. There's nothing like roadmap where you think, okay, I probably do it this way like in 5 years.
We've got some internal discussions about that, but nothing concrete. Really.
Okay, cool, thanks.
Great, thank you.
All right, I screwed up my last question. Luckily, somebody else asked the right one, so this time I took notes. So 2 quick questions and 1 thought. First question, so with your human example on the crossing, do you consider the bounding box movement? If you it makes sense if not, because even Tesla, I don't think it didn't do that.
Wait, I'm just looking for where you are, actually.
Oh, I'm here. I'm here.
Okay. Yeah, so
sorry, I'm like the voice.
So what do you mean by the bounding box movement?
Oh, yeah, so your example of the human on the border crossing.
On the lane line crossing.
On the lane line crossing, yeah. Would you consider the bounding box and the movement of it, like the acceleration or
what do you mean
velocity?
by the bounding box?
For predicting, well, you make the bounding box of the human. You see that there's a human there, right? So you make a rectangle around him.
Oh, okay, yeah.
Like now the movement over time, right? So would you consider that, for example, as to better predict, like with stopping or going, right? Down the line, something like that.
No, so we don't want to do anything like that.
Yeah.
So we really want a fully end-to-end approach. The system should completely learn that a human would slow down or avoid a human, and that behavior will come into the end-to-end system.
Right.
We never want to explicitly track these things.
Okay. Oh, okay. So that goes with my second. That was the thought, like of thinking differently. Instead of like finding out if it's like a kid or adult, you could like do maybe pose estimation, right? Like you could train a model like using epic mega games, meta-human stuff, right?
Right. So that's the kind of stuff we want to avoid. We really want a system that is very simple architecture. You take in training data, behave like a human, so that we don't have to write any of these code or scenarios to deal with any complexity.
Right. I figured you could kind of just make a model that it extrapolates like the movement, right, the skeleton, and then.
Yeah, sure. But the problem is there's an endless list of these things, right? And it never ends. So.
Yeah. Okay. And then last question. It's more for me. Like I work on a VR operating system kind of thing, and the SLAM stuff is really not great. The open source SLAM stuff in some ways. Your system, the sensor fusion and SLAM tracking system, would that work also for like lower velocity and like VR kind of systems, or is it more? For
yes, it should completely work. So we haven't really been able to spend much time into documenting or putting effort into really making this library accessible, but it is open source. You can see how we use it, and I think it has a lot of compelling features compared to other solutions.
Great. I'm going to move to the back of the room. I'll come back to the front. I feel like we had a lot of questions down here.
Hi. So you mentioned kind of the machine learning mantra of more data, bigger models, and you've been working with these models for a while. Do you have any sort of kind of estimation of how big these models are going to have to get in order to reach that goal of driving as well as a human? Or are we not even at the point of estimating that?
I think it's difficult to estimate that, but internally we talk a lot about, what kind of animal would be able to drive a car. Would a cockroach be able to drive a car? Probably not. I think that's kind of the scale that some of the large models people use these days are at, like insect level. I think pretty confident that like a bird or a small mammal would probably be able to drive a car. So if you want to have some very rough estimation, I think that makes sense to think about how many neurons do these animals have that seem to show complex enough behavior.
Great. We also should have plenty of time for everyone's questions, so.
Hi. So you described that the end-to-end approach is essentially predicting the trajectory that the human would take in the picture, right? Mm-hmm. Isn't that, strictly speaking, not fully end-to-end? Because fully end-to-end to me would mean that you record all of the inputs that the human took in the car and then predict those raw inputs from each frame a number of steps into the future.
Yes, so it's not fully end-to-end. I think I glossed over that a little bit too quickly, but we still make the separation between planning and controls. What you're saying is you could skip that as well, just take in video, output the car commands. The problem with that is that it makes it very difficult to abstract different types of cars. So we support all these different types of cars. So we already need some kind of common interface there. That's one reason. The other reason is some level of introspection is useful. If we're just seeing the steering inputs and the gas and brake inputs, it becomes harder to see what the model is thinking. And we really don't think that much is lost in this abstraction layer between planning and controls. It seems like it's reasonable to think that some trajectory is planned, and then you should just always be able to execute that with controls. I don't think there's that much nuance.
Okay.
We're back here.
Right. Similar to a couple questions, but as far as the level 5, and somebody mentioned the model, but I was curious more on the hardware. Do you think the camera and the sensors that you have now is sufficient, or is it going to require like mimicking more like a human, like binocular vision, or only cameras? Or is there any kind of idea of hardware-wise what the future is going to hold?
Yeah, I think there's some limitations to the current system, and there's some reliability concerns, but in general, this isn't the limiting factor. Given the video that the system is getting, it can do much better, and this is true for all self-driving systems. They're limited by the compute and by the software, not by the sensors.
We have another question.
Hi. I'm curious if y'all been thinking about this, or if it's even appropriate, using data visualization or dimensionality reduction techniques to try to peek into the black box of the model, so to speak, a little bit, to see what features of the world your model is starting to learn and pick out for its processing.
Yeah, we've done various experiments with this. At some point, tried to train GANs that try to kind of reconstruct some representation, and We can see what things it thinks are important and stuff like that. But like I mentioned in one of the earlier questions, we've never really had issues trying to understand what the model is doing. With just a little bit of effort, we've always very easily understood why the model is making a certain mistake, and extra introspection wouldn't really help us that much. If it was necessary, we could build more tools, but it's not a huge part of the way we work right now.
Hello, so a quick question. As you're ingesting data into the knowledge base, are you capturing video for all active sessions, or is it simply a sampling of the population? And then secondly, how does my active session benefit from the contents of the knowledge base?
I'm not entirely sure what you're asking. So you're just saying, is all data being used to train the model? No, so we do some kind of diverse sample with some basic logic to enforce some level of diversity, and then we train on that. If we see benefits from training on larger data sets, then we can move to larger data sets, but currently that doesn't seem to be the limiting factor.
How do you plan to gather the context of a curvature?
What do you mean by the context of a curvature?
Whether that curvature is going to, say, do a full 90 degrees, or I don't see how you can understand a curvature unless you have a top-down view, like a map.
I mean, you're talking about the ground truth, or how does the model see this?
I could think that you could ground truth end-to-end longitudinal by using OpenStreetMaps and then using a test track with
No, so this is all just ground truth by using a localizer on human data. We know exactly how a human moved through the world from the localizer, and so that's the ground truth, and that's what we make the model predict.
Does the localizer see the context of the curvature, like the future of it?
Yes, the localizer knows we use the whole future of the drive, so we do know that, yeah.
Hey, has this been tested on pedestrian crossings? Like, does it stop if someone's crossing the street?
So we, as I mentioned, longitudinal currently in OpenPilot isn't that end-to-end yet. We've done some basic experimentation with end-to-end longitudinal, and we haven't gotten that far with it yet. It does react to some things, and it doesn't react to other things. We're still working on that. We only just started really working on end-to-end longitudinal. But I imagine it would react pretty appropriately once we start working on it actively.
So my question is more related to the switching of the lanes. So does the model take into account the state of the blind spot monitoring? Is that input data taken into account in the model?
That's not taken account into the model. I think OpenPilot on some cars, it will just prevent you telling the model to lane change if there is a car in the blind spot. Yeah.
Did I have some questions in the middle? All right, I'm headed back front.
This is a question about the simulator. So you train off policy, and this induces distributional shift, and to account for that, you throw in some noise, which you do with your warping.
Mm-hmm.
For richer, more dynamic multi-agent scenes, like going through an intersection, do you think this approach will scale? What will this work? And if not, do you have to have a multi-agent dynamics model, like Wave AI, where they predict the trajectories of other agents?
Yeah, I mean, well, like we were talking about earlier, it's possible that we need a little bit of a paradigm shift away from this type of warp simulator that we're using now. But I think just right now, it's not really a limiting factor. We have quite a bit of ways to go. And then maybe after that, we can see if there's different strategies that can simulate some more dynamics, for example.
Do you guys use some sort of like self-supervised learning setup? Like, I guess Katharpe in his talk, CVPR, he talked about like how Tesla's like building sort of self-label annotation engine on training examples where the model didn't predict, the accuracy of the prediction wasn't that high. Do you guys see that as some sort of useful pruning of data?
Right now, we don't use that, and I don't think we have a need for it right now.
So in this new, like, what would a human do type of training for your models, are you still like hand labeling for like anomalies, right? When you have a dog that runs in the road or maybe an obstruction, does this new model remove the requirement of that? Like, is there still a use case for comma pencil, or is that legacy now?
So comma pencil has a very important use in the localizer. the localizer assumes that everything in the video is an static environment, and by how that moves, it knows how its camera is moving. So that doesn't work if you assume that moving cars and moving pedestrians are part of the environment. So comma pencil is incredibly important there to filter out the things that are moving through the scene, which are not static, and the static background, which can be used for localization. So comma pencil will always stay for that. Comma pencil also, we get lane lines from that, and lead cars, which is currently still used in OpenPilot, and we can conceive being useful for at least some level of filtering and introspection forever. But the policy will rely less and less on these kind of things as we move forward.
I think you touched on it a little bit, but when your model is making a mistake, I guess I'm just wondering, is generally the confidence high when you're making a mistake? And is there any kind of approaches that you're taking to try to anticipate whether I'm going to make a mistake or I'm more likely to fail?
Yeah, so like I mentioned earlier, the model does predict the likelihood that it thinks a human would disengage or take over, and the likelihood that you are engaged. It's very rare for the model to be confident and still make mistakes. Generally, if that does happen, that was due to some crazy data bug that we've fixed. I can't remember seeing any cases like that recently.
This is a bit of a philosophical question, because from what I've gathered, it seems like you guys are trying to build a model that behaves like a human more than just like an object prediction model. What impacts do you think this will have on AGI in the future, say like 5-10 years from now? Do you think it'll help out with that at all? Or do you think it'll make it more possible?
I mean, I think this is just a step towards AGI. I think this is more, more generic machine learning that will scale and sometime might create superhuman AIs.
Hi. So first a comment. I work at Wave AI, and we have end-to-end lateral and longitudinal. But
Okay.
You're right that yours is the only one you can buy and try yourself.
I appreciate that.
I don't know if you could have seen the videos in the CVPR workshop we had.
I think I've only very briefly seen things. I don't think I really looked into it.
The question, you mentioned that most of the stuff you've been doing to improve the model is improving the ground truth. But if it's end-to-end, I'm not sure what ground truth you're improving. Is that just failures of the localizer?
Yes, pretty much. So the localizer failures, they can fail in many different ways, mostly because how much of it relies on video, and you have all these different types of driving scenes. So we didn't talk that much about the localizer, but we started 2 open source projects based on it. So it's clearly a big part of what we do. Probably spent 2 to 3 years really iterating through the localizer, making sure that it's robust. You have other SLAM systems like OrbSLAM, stuff like that, that is very accurate and works most of the time, but they tend to fail in rare cases, which are still not that rare and need to be fixed. So we spend a lot of time working through that.
We've got another question upstairs.
Hey. I'm just curious if the self-driving models that you're using primarily seem to be used on highways, and I think of driving in general to kind of really be split into highway driving and sort of city driving with stop signs and people and stuff like that. And I see those as 2 kind of distinct problems. Do you think that the models that you're building now actually can work safely in city environments, or do you see any challenges looking ahead to level 5 in that regard?
So we currently focus on highway driving just because it's the most useful. We want to make self-driving cars, but we do want to ship cool and useful things along the way. I don't think there's anything in this strategy that's inherently limited to highway driving or any specific scenes. I think it will scale perfectly fine, but it is significantly harder to drive in the city, I think, than on highways.
Hello. Got a question over here? I have a bit of an open-ended question. Do you guys see any differences in the average of the way that people drive in Tijuana and LA and San Diego?
I can't say I've ever looked at the differences between cities, but there's certainly a difference between continents.
Hi, I have a question. Since you say you finally let a human kind of teach the agent to learn how to drive, so when is the day comma plan to let us to teach it when it's not working?
I mean, implicitly that already happens because when a user disengages from the system, that's a signal that the user wasn't happy with the way it works. So there's already this kind of feedback loop. We have very good ground truth for when a user didn't think the model should drive. So we actually have very accurate metrics on how confident people are in what it's doing.
Great, we're back here.
Hey, Harold. In your blog post on lateral planning, you talk about ways that the model will cheat in the simulations. Could you go through some of the ways that y'all detect and mitigate against the model cheating?
So just quickly on that, when we move around in the simulator, the image warps, and this can be detected by the model, which is what the cheating is. So one of the ways we can detect that is by introducing warp without actually having real data. So we can have fake data, introduce warp, and seeing if the model reacts. And so we have tools like that that allow us to measure some level of cheating, and we had some introspection into that.
Great. These are our last three right down here.
I wanted to ask how your model training process scales or doesn't scale, and this is my ignorance on machine learning in general. When you iterate on your model, are you throwing away the previous model and starting again from scratch? Like if I had a new human driver, 16 years old, and they had a collision, they would learn from that and move on and become a 17-year-old driver instead of a 16-year-old driver. But I'm curious if you have to start that over, and if that has implications for scale and the kind of long tail of weird little problems you have to figure out to reach true self-driving.
Right. So yeah, so that's an interesting question. Currently, we train everything from scratch most of the time. It doesn't cost that much time, so it's not really a reason to try to avoid that. Maybe in the future, the training is so costly that it makes sense to start training incrementally. But I don't foresee that happening soon. We don't seem to be that limited by the size of the models right now. But if we do have to scale the models to get the performance we want, then maybe incremental learning is what we want to do.
More GPUs.
I know that eventually you want to get to level 5, and ideally you would be there tomorrow. And then on the other hand, some companies seem like they'll maybe never get there, like Waymo. What's what primarily is influencing the velocity of your model improvements right now? Like what work inputs do you find are like the biggest barrier to getting to that next major milestone for you right now?
I think if I were to list one limiting factor, it would just be the infrastructure to test the models in how well we can predict that they perform. So if we have tests we can run immediately on a trained model and immediately says it messes up in these ways and it's good in these ways, then it's very quick to iterate on that. And I'd say it's building these tests and building these metrics that is very time consuming, and if you mess it up, it costs even more time because you find out later and you have to go all the way back. So I'd say the quality of how well we can evaluate the driving offline with tests, I think, is one of the limiting factors.
So you mentioned this bug that you had with the mapping continuous lines to themselves in the visual odometry. How did you fix that bug?
So we fixed that bug in particular by doing some basic filtering on the orb features that are tracked. So we do have a gyroscope, which tells you how the car is turning, and we have some GPS data. Neither of those are accurate enough by themselves, but they're accurate enough to just do some basic filtering, throw out really bad orb features, and then the ones you have left are good enough to deal with the rest of it.
I'm coming. So Harold told you guys a lot of things today, but there's one thing that he didn't tell you guys, and that it's his birthday today. So will you all join me in singing happy birthday to Harold? Happy birthday to you. No, you're two. To you. Happy birthday, dear Harold. Happy birthday to you. Yay! Okay. I think we're going to say goodbye.
I was going to try to eat this with my hands, but that seems like a mistake.